I think there's still more folks streaming in, but it's stabilizing a little bit. Let's get started. Good morning, everyone. Welcome to another exciting installment of LlamaIndex webinar. I'm Simon from LlamaIndex, and in today's installment, we're going to go beyond top K retrieval and explore the latest tree structure indexing and retrieval techniques proposed in RAPTOR. RAPTOR is a recent paper published in iClear 2024, and we're super excited to host authors to give us a deep dive into the latest technique. So here we have Parth, Anna, and I believe Aditi as well. So please take it away, Parth, and hand it over to your co-authors as necessary. Go ahead.
Yeah, sounds good. Thank you for Can you see my screen?
Yep. Thanks. And if anyone has questions, please put it into the chat, and we'll have a section at the end to answer all the questions. Thank you.
That's good. Hi everyone, I'm Parth. Here with my fellow co-authors, Salman, Atish, Shib, and Anna. This is RAPTOR. So RAPTOR stands for Recursive Abstracted Processing for Tree Organized Retrieval. Super excited to share this with all of you. So let's get started. So I like this slide from the ACL 2023 tutorial on retrieval-based language models and applications about all the exciting questions in the realm of retrieval augmented language models. I know LlamaIndex has been working on a lot of them too. So it's interesting to see the three questions that they frame here on what
मम्मी का पानी
on what to retrieve, how to use retrieval, and when to retrieve. So RAPTOR sort of falls into this what to retrieve end on the text chunks. And the aim of RAPTOR is to retrieve text chunks that give an holistic understanding. So if we sort of look at retrieval augmentation in the current retrieval methods, the way it generally works is that the way you get these text chunks is that you have a retrieval corpus, and then you split it into chunks. You can split this smartly using all the fancy chunking techniques, or you can just split it at 100 token level. You can make sure that your sentences aren't being cut. And then once you have these text chunks, you use some sort of BERT-based encoder to encode it into different embeddings. And at query time, you get a query, you encode it using the same BERT-based encoder, and you do cosine similarity. And you have your top K, so depending on what your top K is, you give the highest ranked sort of text chunks as context to a language model. Normally you give it in context to the language model. So we're all very familiar with this sort of retrieval paradigm, but why might this be an issue? So let's sort of look at an example. Let's consider the question, what is the central theme of the story? And if we look at relevant chunks from this story that we're doing this question on, you can read the chunks. It's like, 2 mice turned into footmen, the clock had struck 11, they did not notice Cinderella. You can imagine this is from the story tale Cinderella, and you ask the question, what is the central theme of the story? You get these chunks and you pass it to your language model, and you get this amazing answer, right? The theme of the story is centered on jealousy, cruelty, justice prevails in the end. The story is about Cinderella, conveying important moral lessons about the consequences of wickedness and the power of kindness and perseverance, right? So seems perfectly fine, seems like a great answer, but there's a twist. So the story that we're sort of dealing with is actually a modified version of Cinderella, where in the end she becomes a tyrannical queen. So, if you look at the answer here, it's completely wrong. It's not about how the power of kindness and perseverance sort of, wins over wickedness. In fact, it's more about how, the story, the consequences of mistreatment and abuse lead to the cycle of cruelty. And you can sort of look at this RAPTOR answer on the same story, and it sort of gives this answer. And So the question is, how let's in this presentation we'll dive into how do we sort of get we'll talk about how we get a tree structure which is able to capture both this higher level and lower level information. So the insight over here is that you need some higher level information about your retrieval corpora that can help us answer thematic questions, do multi-hop questions, and better understand what your retrieval corpora entails. And you obviously need the lower level information for creating this higher level corpus, but also to also answer questions that you can sort of answer with one chunk. What is the name of Cinderella's stepmother? You should be able to answer probably with just a single chunk. So this is our insight that we need both higher level and lower level information, and let's dive deeper into how we get it. Just as a quick aside, there are models that are coming out every day. So in recent weeks, we've had Claude 3 and Gemini 1.5, and all these questions around RAG and long context models. So there are a lot of opinions on this. I'll just share like two small points about this. Obviously models sort of there's this paper called Lost in the Middle, which sort of shows that models struggle to effectively use long range context, especially when the information is buried in extensive text. So even if you have if you just have around 4,000 tokens, depending on where the information is, you get widely varying accuracy. And secondly, use of long context is expensive and slow, right? So if I found this amazing picture on Twitter which shows that if you pass 1 million tokens on like Gemini Pro 1.5 is around 50 cents per call, whereas if you just use RAG, you can significantly reduce that cost. So it's long context are expensive and slow, and they might struggle with your information if it's buried in extensive extensive text, and also your retrieval corpus may just be larger than a million tokens. So let's dive deep into how RAPTOR works. So RAPTOR is this technique that sort of uses clustering and summarization to create a RAPTOR tree, and we retrieve from this tree at inference time to provide both higher level and lower level information to your language model. So how do we build a tree, right? So we start by having this tree, and we build a tree by starting off chunking your retrieval corpora normally. So you can use any sort of fancy chunking methods if you want. In our experiments, we just decided with a very simple chunking strategy of chunk every 100 tokens, but don't split sentences across different chunks. And you can RAPTOR is chunking agnostic. You can use whatever sort of chunking method you want. And once you have the text chunks of your normal retrieval corpora, we cluster the text chunks based on a clustering algorithm. And once we have these text chunks that are clustered into different clusters, we pass it to an LLM to summarize it. And then we get the next layer of our text chunks with the relationships between the child nodes. And we sort of recursively apply this again. So we again cluster it, we embed it, and then we cluster it, and then we summarize, and we keep on building this tree till we're no longer, either we get to a root node or we're no longer able to cluster anymore. So if we have, let's say, three nodes at the root layer and we can't cluster anymore, so we keep on building this tree till we're not till either we have a root node or we're no longer able to cluster. And once we sort of have this tree, we can query from it. So just some quick motivations for the clustering algorithm that we're thinking about. So we wanted soft clustering in our clustering algorithm. So the insight being a chunk that covers multiple topics should appear in summaries for each of the respective topic. For example, let's say I have my retrieval corpora contains text about, let's say, Parth is a singer, Simon is a singer, Jerry is a singer, and then it has a few sentences about how Parth is a violinist, Anna is a violinist, and so on. So you might want our nodes to have one node might talk about Parth, about how Parth is a singer and Parth is a violinist. one node talking about violinists, about how Parth is a violinist and Anna's a violinist, and one node talking about singers, how Parth is a singer, Simon's a singer, Jerry's a singer, and so on. So we sort of want this soft clustering in our system so that our nodes are able to cover chunks that have sort of multiple topics in them, right? So we want when we're sort of our summaries should contain all the information, and you shouldn't restrict your chunks to just be part of a single parent node. Secondly, we don't want a number of clusters to be predetermined because it's sort of hard to know ahead of time how many topics are in your document. So we want a clustering algorithm that is able to decide at build time how many clusters you need. And thirdly, you sort of want every point to be assigned to one cluster, even though if it's present in your leaf nodes, that's fine. But in general, you probably want some sort of path from a single leaf node to any other leaf node, so that you're able to we'll see in our tree traversal methods that you're able to sort of get from one way to another, and you have some sort of from any sort of root node, you're able to get to any sort of leaf node. And you don't want information to get lost and be incorporated in your tree structure. So the clustering algorithm that we use is the following. So first, we reduce the dimensions of the data using UMAP, which is a dimensionality reduction technique. And we use UMAP for sort of dual clustering. So we first form global clusters using UMAP, and then we form local clusters. And within each of the global clusters, we use Gaussian mixture models as our clustering algorithm, which gives us the respective clusters that we then summarize. And we tested it against this sort of spatial window-based groupings and k-means clustering, and GMM performs better. And we welcome new work on this. So our clustering algorithm worked really well for us. But there are definitely improvements possible on this, and we actually look forward to what people sort of come up with different clustering algorithms.
Hello. Hello.
मीटिंग में हो?
नहीं, मीटिंग में नहीं.
So once we cluster the nodes, the next step is summarization. So once the nodes are clustered, we pass it to a language model to summarize. You can choose any language model you want. In our experiments across the data sets, we chose GPT 3.5 Turbo, a very effective model. And we saw that just looking at some of the numbers empirically, we saw that it's a 72 GPT 3.5 is able to do a 72% compression rate. So the average ratio of the summary length to the sum of the child nodes length is 0.28. And with summarizing, there are obviously concerns about hallucination. If your model makes up something that is not in the child nodes that you provide, and this is a concern. So we wanted to sort of test for this and how frequent is this hallucination concern. So we ran an annotation study, and we randomly sampled 150 nodes across 40 stories and evaluated them. And we saw that the hallucination rate is relatively low. We only saw out of the 150 nodes, only 6 nodes had some sort of hallucination. And it was minor hallucination. It was mostly due to the model sort of adding in extraneous information. So if the model sort of knows about the topic, it might add its own information to it. So the information wasn't correct. It's just not that it wasn't in the child nodes there. But this was relatively small, so hallucination is not really a huge concern. And with models getting better, I think this will be something that hopefully will be solved soon. Yeah. And let's sort of look at how RAPTOR scales. Obviously, computational feasibility is important, and it's great that RAPTOR sort of scales linearly in both your build time, so it doesn't have some sort of quadratic factor to it, and also in the number of tokens that you spend, because obviously you are summarizing your retrieval corpus, so you want to ensure that you don't make too many queries, so it scales linearly in the size of your retrieval corpus. And this is because, as we sort of saw earlier, that the compression rate is 72%. So the amount of tokens that you pass into your model, you only get 0.28% back as your output token. So it scales linearly, and that's why it's sort of computationally feasible. And we ran all of these experiments on like a 16, I think on a 16 GB of RAM, like Apple normal M1 computer. So these aren't run on some very fancy GPU, just your everyday consumer electronics. So it's feasible. You can sort of build the trees on your own laptop, and you can use Raptor. So once we build our tree structure, now you want to query from it. And there are two methods that we explored: the tree traversal method and the collapsed tree retrieval method. So the tree traversal method, the way it works is, you sort of traverse the tree from the root nodes all the way to your leaf nodes. And the way it works is that let's say you decide the beam size, or how many nodes are you going to keep at every level, and your depth size. So do you want to retrieve only the first two from the first two layers, or till the end, right? And the way it works is, so at the root node, you sort of do some sort of similarity search or vector-based similarity search. And let's say if your top k is just 1, so you keep your the top chosen node, and then for the next layer, you only look at the subset of nodes that are the children of the first layer of the node that you've chosen, and then you do similarity search over just these children nodes. And let's say you get, for example, in this, you again choose your k nodes, so here top 1, and then you again just look at the children of that node, and then you sort of choose your node, and this forms your retrieve context that you pass to your language model. On the other hand, the collapsed tree retrieval, much simpler. You essentially collapse the entire tree into a single layer, and you run similarity search on the entire tree at once, effectively. And then again, here you can sort of see top 3. So your normal similarity search, and you choose the top 3 chunks, and you pass it to your language model again as context. So what are sort of the trade-offs of these two approaches? And in our experiments, the collapsed tree approach performs better. So you can look over here. The green curve is the collapsed tree approach, whereas this one is the tree traversal approach. And the reason for this is that collapsed tree naturally provides more flexibility for tree traversal, since you're searching across all nodes simultaneously. So you can, if it's a thematic question, you might sort of retrieve nodes that are more towards the top level, versus if it's a more granular question, you can retrieve nodes at the leaf level. And tree traversal, on the other hand, if you choose consistent values of your depth and your beam size at each level, it keeps a constant node ratio, right? So at every level, for example, you will only choose one node at every level. So it keeps an equal amount of information of lower level and higher level nodes. So this is like question agnostic. So not like, depending on the question, you're not changing the values. But I think the benefit of tree traversal is that if you do know what your questions are going to be ahead of time, or if you know that you're going to be querying just on the leaf, just on a thematic question, or just on a question that is more granular, then you can sort of change your start layer, you can change your beam size, and you can choose the layers that you're going to retrieve with more effectively. So in our experiments, we didn't want to tune it, so we use collapsed tree, and that performed better. But if you're using this in practice and you have an idea about what sort of questions your users are going to ask, then based on that, you can sort of decide if you're going to choose a higher level node or a lower level. You're going to choose to retrieve from layers that are on the top or from layers that are on the bottom. So let's look at contribution of the tree structure. And just a small thing over here is that in our experiments, we saw that when you compare it against your normal traditional retrieval augmentation methods, we saw an interesting thing that every time, anytime Raptor sort of, if for the same question, the nodes that Raptor retrieves and the nodes that your normal traditional augmentation method retrieves, we saw that Raptor always has at least a parent or an ancestor in its retrieval in the chunks that it retrieves from the nodes that your traditional retrieval augmentation method retrieves. For example, if you look over here, if for example over here your traditional DPR, in this case your traditional retrieval augmentation method, retrieves this node, but you also see Raptor, for example, retrieves its parent node. So the higher level nodes will in collapse tree, your high level nodes might always have a path to a lower level node. So any information that is empirically, we saw that any information that your normal retrieval augmentation method retrieves, we have a node that has the same information in the form of the summary. And so we were looking at, we validated so the number of tokens sort of range all the way from, I think, 16,000 around, I think, 2,000-3,000 stories, and we tested on quality, which is more medium length documents. So it's around 5,000 on average of 5,000 tokens, and then Casper, which is question answering on actually NLP papers, and so that has an average token length of, I think, 19 to 20,000 tokens. So we're looking at 3 data sets, and we were building these trees, and we were retrieving using the collapse tree approach, and we were sort of curious to see where are the nodes coming from. So interestingly, we saw that around 30% of the nodes are the higher level nodes, and the rest are sort of leaf level nodes, right? So it's interesting that it's only sort of 30% of the nodes are necessary or were being retrieved that are from the higher level nodes. So we're looking at how much do these nodes actually help our system. So if you look at the tree structure, we sort of see if you just retrieve from your layer 0 or your leaf nodes, you get, let's say, 57% accuracy on this. But as you add more and more layers and you start retrieving from all these layers, you can see that the quality consistently increases across this. So this is from 3 random stories. We have, look at our paper, we have a lot more stories there, but you can see the general trend of, as you add more layers and you retrieve across all of these layers, you can see an increase in accuracy from 57 to 73 here, 66 to 83, and then 57 to 68. And it's interesting that if you look at these results, if you, let's say, only retrieve from an intermediate node, let's say you only retrieve from layer 1, you can sort of see you effectively match the performance of just retrieving from layer 0, or you're close to that performance. So another thing might be, if you recall, that layer 1 sort of has significantly less number of nodes as layer 0. So just by sort of creating these synthetic chunks or just summary chunks, you can even match the performance of your layer 0 nodes. So one interesting thing over here is that if your retrieval corpus is really big, and although similarity search with face is really fast, if you sort of want to reduce the number of chunks in your corpus, you can effectively just cluster and summarize, and then just retrieve from that node. But obviously, adding more and more layers and then retrieving from all the layers helps a lot, as you can see here. And Raptor also has state-of-the-art results on the 3 data sets I mentioned. So on quality, it's around 80% accuracy. On narrative QA, on the Meteor benchmark, we have the state-of-the-art, and on Casper, which was long-form question answering on LP papers. So one interesting result that we saw in narrative QA is this result with the recursively summarizing books model. So this was a paper by OpenAI a few years back, where they sort of just based on the window or spatial positioning, they sort of grouped and summarized their summarized the chunks, and they were just using sort of the top level nodes as context for their model, and it's evaluated on the sort of the same model and the unified QA model. And we see that just looking at these numbers, you can sort of see a big boost in accuracy from just using all of the nodes, the intermediate nodes, rather than just using the top level nodes. So the intermediate nodes certainly help, and obviously this is based on spatial positioning, on where just clustering or just grouping together nodes that appear together in your retrieval corpus, whereas we're using a clustering algorithm. So how to get started with Raptor? So you can check out the Raptor GitHub at this link, and you can get started. Raptor is also available on LlamaIndex, and you can use that too if you're building LlamaIndex. And there's also this great LangChain tutorial on Raptor and Claude 3. So actually, funnily enough, it seems like long context plus retrieval augmentation might give you even more benefits, just rather than just using either long context or retrieval augmentation. I think them together really form a deadly combo. And some concluding thoughts on this. So, tree retrieval, as we saw, gives our retrieval system both high level and lower level information about our retrieval corpus. This, outperforms just methods that rely on the underlying raw text, and the synthetic chunks really help a lot and provide a more holistic understanding of long documents. And we're super excited to see what everyone builds with Raptor. So thank you. And if you have any questions, love to hear them.
Thank you so much, Parth. That was a great presentation. I definitely learned a ton from that. I think we have a lot of questions in chat, which we'll try to read over and paraphrase. And we'd love to hear your take on some of those. I think most of these are specific to the paper. I also have a list of questions that I would love to hear just your general thoughts about the space in terms of RAG, research, long context LM, which I'll try to get into afterwards. I think the first group of question, so there are a bunch of them on the chat, is about the clustering algorithm. So we'd love to hear a little bit more just intuition about the clustering algorithm. And for example, I think a specific question is, isn't a document a cluster of paragraph in itself that has more meaning than a cluster of paragraph on the same subject from multiple different documents? So I think what the question is getting at is the document itself has some semantic connection between its constituents. So it might be a good way to group these segments to begin with, and how to think about this in the context of having a large corpus with multiple documents, which you're building these clusters on top of. I'd love to hear your thoughts about, in general, these different paradigms in dealing with one document or multiple documents over a large corpus.
Yeah, sure. I mean, that's a really great question. So if we sort of go back to the clustering algorithm, I think we wanted so if you have sort of documents that have the spatial thing, so if they're within the same document, they probably have a high enough cosine similarity that the clustering algorithm itself will catch that and will group them in the same cluster. Secondly, you can obviously, and we played around with this in the beginning, you can sort of add a both spatial and a clustering based approach. So you can very easily incorporate that you want a certain window size and also a certain cluster. You want the chunks that you sort of get the chunks that are within the cluster to summarize. So you can sort of add both. We noticed that if you just do clustering, it itself sort of captures that. So there's no real need of being explicit about choosing documents that, or paragraphs that are close to, are within the same document or are within the same thing. So the clustering algorithm sort of automatically, because if you think about documents that are chunks that are in the same document, we'll probably be talking about similar things. So they'll automatically come within the same cluster.
Yeah, that's super interesting. And just to clarify, when you build these clusters, they contain chunks across different documents. Is that correct?
Yes, so whatever text you pass in, it'll contain all of that. So if you pass in multiple documents, it'll contain chunks across the different documents.
Gotcha. I think I just saw a follow-up question that's specifically about this. Like, if you have two separate documents, for example, one is this financial report about 2021 and the other one is about 2022. And if I ask specifically about 2022, how to make sure the retrieval doesn't pull information about the 2021 report. I think that's sort of related to this discussion topic.
Right. I think for that, you may want to so there are a few ways of doing this. I think one way is obviously, if you have metadata, you can incorporate that. Secondly, I think what might be interesting in this case, what I would do if you have sort of an updated, so we're working on actually how to sort of update these trees. But secondly, if you have reports on 2022 and 2021, what you can very easily sort of do is, you can look at the nodes and you can look at the paths. So if there's any path from the 2022 nodes and from any path from the 2021 nodes, you can just ensure that you only take nodes that have a path from the 2022 nodes. But updating the trees is an ongoing work, and we're excited to have something for you in some time. Yeah, for that. Good question.
Yeah, that's actually going to be my next question. How do you add new documents to these indexing algorithm? I know it's going to be a follow-up work. I'd love to hear a little bit about just your high-level intuitions and what are the directions you might explore.
Sure. So I think one very interesting sort of paradigm that we're exploring is this. So using the tree traversal nodes, you can sort of figure out what nodes at every level are semantically closer to your nodes, right? So you're to a query, for example. So the line of work that we're sort of exploring is that if we have a retrieval corpus that is that you have new information, you can figure out what are the nodes that are going to be impacted with this information, just based on similarity. And then once you figure out what are the nodes that are going to be impacted with this, you can re-summarize them with the new information. So and you can add a path to the leaf nodes. So that's sort of the line of the work that you can do. So you can figure out the nodes that are going to be impacted by your new information and then only update those nodes.
Gotcha. That makes a lot of sense. I also saw in the chat a lot of questions about like interesting examples or visualizations as it relates to the clustering and the retrieval aspect. I'm curious if you have looked into sort of specific queries and how that's kind of like being, what are the document that it retrieves and what are the clusters that actually look like with respect to those to help Raptor achieve the performance improvement.
Yeah, so I mean, we have some examples in the paper, so you should definitely read the paper. Secondly, so we're actually working on this visualization thing, so you can just call, raptor.visualize or aria.visualize, and we'll make this amazing diagram for you using some graph libraries. So I think that should be going out soon, so you should stay tuned for that. So then you can sort of visualize all the paths and all the things in itself. But the clusters that we saw, for example, so like one thing we saw that with the contrived example that I had, like Parth is a singer, Parth is a violinist, Anna is a violinist, and so on. You can sort of see that depending on the topics, it's really good at picking out different topics and then summarizing it on topics. If you look at the clusters themselves, they're pretty topical in nature, which is very interesting. But you can do that yourself using just so if you're using the Raptor GitHub, for example, you can ask it to return the layer information, and you can look at the nodes itself, but we're also working on a visualization tool, so that should hopefully you should be able to see some really fancy diagrams and how the tree is being constructed.
Sounds great. Yeah, I definitely will personally play around with it a little bit more to understand sort of the behavior and the clustering. Another follow-up question, this is about clustering as well. Like I think Gans is asking about right now we use summarization as the main operator to apply it to the cluster of documents. And the goal is to support like downstream QA that needs high-level context, right? Do you have any other thoughts on other type of operations on these cluster of documents that can support different use cases, perhaps?
Right. So I think once you have clusters, I definitely think depending, you can definitely add, to your summarization step, you can definitely add more sort of like more context to it. So one sort of thing that I was just thinking about yesterday, it might be followup. It's like, so this is completely, like some discussion I was having with someone actually. It's like, what about code RAPTOR, for example? So if you want to do this on code, maybe then, you may not want just sort of summarization of there, but you might want to sort of have you might want to have sort of graphs that the clusters sort of represent function calls between each other. So you definitely there definitely is followup, like potential ways of sort of improving other algorithms. So you may not want to summarize your functions, but you may want to just definitely have some sort of graphs or paths from one function to another. So something like that might be interesting to solve like GitHub issues, for example, maybe.
Yeah, that's super interesting. That's my next question. And also coming from the audience, right? Like, the question specifically was about code, but I think in general, the concept of like the richness of different documents and different type of granular semi-structure nature is very interesting to play with in terms of these kind of hierarchical retrieval techniques. And I think like another top of mind challenge for a lot of practitioners are like dealing with tables in these like PDF documents as well as like rich media documents. I'm curious if you have thought about, like in the context of not just like plain text, but having a little bit more semi-structured components inside, how does that interact with this hierarchical retrieval and summarization approach? Curious to hear your thought.
Yeah, I think if you have, images and tables, I know there's a lot of, you can be very easily sort of incorporate with RAPTOR. I know there's a lot of, I think, chain of table or something on those lines. There are like papers that are able to extract information from this. So let's say image, you can pass it to all these models today that can take in image inputs. So I know Gemini can take in image inputs. You have obviously GPT-4V that can take in image inputs. So it'll be interesting to what you can sort of do is that you have, for clustering, you have models that actually are able to embed images in the same space. For example, clip, right? So you can embed images in the same space as your text. So you can actually cluster images too. And then at the summarization step, what you can do is for models that sort of support images, you can actually pass in your image and your text together, and you can ask it to summarize the image, what is the things inside the image, and also use the text. You obviously use your text chunks too. So I think they're definitely, I think it's a great idea. So you can actually definitely sort of add images, and so I think there's also work on the lines of embedding tables and so on. So you can definitely add that with RAPTOR. But yeah, definitely very interesting line of work there.
Well, thanks for the great answer. I think like we had a webinar on sort of table QA before, I think in the previous one. So definitely a lot of very interesting research there, and sort of the integration of those table reasoning and retrieval and sort of these hierarchical and clustering type of work, how that work together is a very interesting research direction in my mind. Sort of changing topic a little bit, sort of still related to sort of this grouping and retrieval concept. I think a lot of challenges in practice is dealing with documents that either like it's ingested across time or updated across time, right? So you can imagine like a knowledge base that have, like documents from like 5 years ago, 2 years ago, this year, which might contain similar topics. And oftentimes people want to retrieve the most, relevant information that's like recent, right? Have you thought about how to kind of give the ability to control this like sort of boosting or re-ranking aspect when it comes to time, and how that relates to clustering and grouping of this information?
Yeah, I think for more recent things, if you're summarizing it, I think what you can simply do, and I haven't tested it, but what you can simply do is just sort of add your information about time to it. So for example, let's say I created my tree on something that is from 2021, and now I have more documents from 2022. If I just prepend, this document is from 2022, and you prepend that to every chunk. So then when the model is sort of summarizing it again, so it sort of knows this is from 2021 and this is from 2022. So it'll sort of, in the summaries, it'll sort of like say that, okay, so from 2021, this thing, and from 2022, this thing. So when you're retrieving chunks, you will have chunks that have information. So only the chunks that, again, so when you're updating the tree, and only the chunks that have are the chunks that will be updated are the chunks that sort of need to be updated, right? The thing that I'm trying to get at is if you have chunks that are not time dependent. So I have some information in 2021 that remains the same in 2022. Those, if my report about 2022 will does not contain any information about those things, it'll remain the same. But based on your cosine similarity, if I have information in 2022 that gets updated, so the chunks that are being updated are the chunks that have that information. Therefore, you can just prepend some time information and update it like that.
Gotcha. Thanks for the great answer. I'm just checking for the latest question on the chat. So Bram asked, how costly is the method? I know you have some like high level sort of takeaway you shared up via the slide, but we'd love to hear maybe a little bit about the trade-off in terms of like amount of additional compute required to do this method, and like what are the scenarios in which like this is best suited for to help a practitioner choose like different techniques for their use case.
Yeah, I think that's a great question. So how many tokens? I think you can sort of roughly estimate it pretty easily. So as I said, your compression rate, if I go to the summarization step, you can sort of see, it summarizes 72% of your thing at every level. So you can sort of bound it by around, I think, like a factor of 2 or 3 sort of tokens. So if I have a retrieval corpus of 1,000 tokens, I know the input plus output tokens. So if there is 72% compression rate, I sort of know it's like bounded by around 2 or 3n. So if that is the amount of 1,000, if I'm using 1,000 tokens, I know that my input plus output tokens are roughly going to be on the order of like 2,000 or 3,000, simply because you have soft clustering, so it might be a bit more, but you sort of know the bound on it. As for computational things, so we ran our experiments on a normal Mac, right? So just a Mac with 16 gigs of RAM. So it's definitely feasible to build sort of these trees on your laptop. And if you have access to better compute, then obviously you can sort of use that. But just on your Mac, we've created trees that that go up to 400,000 tokens. So pretty big trees about like long stories and so on. So I think it's definitely computationally feasible to do it on your own sort of compute. And if you have access to better compute, that's better, but obviously. But it's definitely feasible to just do it on a consumer grade laptop.
I think the other thing is that it's an offline process, so it's one and done, right? You can create some tree for a set of documents and you can just reuse it over and over again forever. Maybe you update it.
Yeah, that makes a lot of sense. Thanks, Hannah, for adding on. I'm just scrolling through the chat to see if we missed anything. If anyone has a burning question, please raise your hand or unmute yourself and ask. But I do have a bunch of like higher level questions that I would love to brainstorm with the others.
Yeah, sounds good.
Cool. Maybe one of the biggest like question I have is just aside from the sort of concrete question we talked about, is there any other future directions that you guys are thinking about that you'd like to share beyond sort of some of the questions we just asked?
I mean, I think, adding information is definitely one, but I already talked about that. I think improvements to the clustering algorithm in general. So right now we use, GMMs. So GMMs, assume that your text is Gaussian, which we saw that empirically, like text is more sort of sparse and skewed, but it worked really well, empirically, but we're sort of, exploring maybe approach that might be more so, that might be, for example, GNN based, right? So it might be using a graph neural net to actually form the clusters, as opposed to just using Gaussian mixture models. So we're exploring on the lines of improving the clustering algorithm. Secondly, I think you gave us a great idea about looking into how you can use visual information. So I know images, using images or tables and so on. If you can embed it and you can pass it to your language model, you can use Raptor with it. So it'll be interesting to sort of see, using information and tables with Raptor. But I think updating the tree is probably like a very, very heavily requested feature. So that probably has our attention on it for now.
I think someone in the audience raised his hand, so I'm going to ask him to ask the question, him or her. Right.
Hello. Yes, thank you so much for this webinar, very useful. I have one question, specifically about the data set. Like, I'm not sure like how to like explain this exactly, but like what we are trying to do is use a large code base, like analyze large code bases, and like specifically function by function. So we kind of want to be able to have a summary of a function and then like find all the dependencies that are being called in this function, or where this function is being called, and also like traverse the tree and summarize like everything. And then at the end, basically gave an explanation what this part of the code is doing, or generating the documentation. This is specifically very useful for old code bases. And I was wondering if Raptor is something that can help us. Thank you.
Yeah, I think code is definitely very interesting and something we're also thinking about, as I mentioned. With code, so if you don't want to if you just want to explain things, or if you just want to use the information as to find out some things, then Raptor as is should be useful, because it is going to summarize. So if you use Raptor with code, it's going to summarize what your functions are doing and so on. It might build sort of this tree structure. So an interesting thing would be, I'm not sure, I haven't tested how well clustering algorithms sort of work on code, but there, for example, but you can definitely fine tune just normal bird-based encoders on code. I think Colbert, for example, their repo supports just passing in custom data sets and then fine tuning on that. I think the interesting thing over there is, so if you're just sort of using it to answer questions and not exactly run the code, then you can definitely use summarization. And obviously function calls within themselves have a hierarchy within them, right? So I have a main function which is calling my other functions and so on. So I would imagine the clustering algorithm picking up something like that. So for example, if you have a function call in one function, that probably will have a high similarity. For example, if I have function A calling function B, and then a function C also calling function B, since they're both calling function B, they will probably have a high enough cosine similarity. They'll be grouped together. But I think using the information in it without explicitly clustering it might be, so if you want to run the code and if you want to sort of have this hierarchy, you can sort of use that as well. And that's something that we're also planning on exploring. So if it's just, the short answer is, if it's just answering questions, I think Raptor just as is should work pretty well, because it will cluster things that are calling the same function and so on together. But it'll be interesting to sort of incorporate the natural hierarchy in the code base itself, and that's something that we're also planning on exploring, but we'll be excited to see something from the community on that.
Yeah, it's a very interesting discussion. I think in terms of different document type, there's a whole spectrum of like unstructured to fully structured. And in my mind, like there's different aspects of leveraging prior-free clustering versus like more structured traversal that uses the inherent structure itself in that document. I think this kind of like gets me into a particular question. Like there's no good answer to this, I think. Otherwise we would have solved this already. But like different type of questions and different type of queries can be like inherently very, very different tasks, right? And I think like one of the promise of large language model and some of these structured retrieval techniques, we're basically saying that like there might be a good general way to do some of these that cover broad spectrum of tasks, right? I'm curious about your thoughts in terms of like crafting domain specific retrieval techniques that target specific document types and query types versus like trying to approach a more generalist way, right? So is this like almost like, do we get AGI to solve this for us, or are we going to still go into a more crafting individual modules and routing to the individual modules, right? Like I don't pretend I know the answer or there's a good answer. Would love to hear your thoughts here.
Yeah, I think for domain specific things, the way you can sort of improve performance on different queries is one, just having sort of better embeddings model for sure. So if you have some sort of data set and you want to use so the embeddings model that we use are very generally trained. So SBIRD has been trained on a lot of different sort of types of retrieval corpora. So it's very general, but if you know the sort of retrieval corpus ahead of time, you can definitely fine tune your own embedding model so the clusters are better and so on. Secondly, I think so it depends on if you have insights on what sort of questions you're gonna ask, then as I mentioned, you can sort of tweak the parameters of tree traversal and so on. And one interesting line would be to not do this by yourself, but actually just ask a language model. Is this a higher level question? Is this something that needs more lower level information? So I know there's a lot of work being done on creating queries using then creating like fake like either multi-hop queries using language models. So an interesting thing here would be to ask a language model to either create, depending on what sort of the query is, to you can obviously ask it to create higher level queries that might answer this question and then restrict your tree size to above, or you can sort of create low level queries and just make you can choose the layers in the tree that are more low level. So you can definitely, depending on what sort of thing is, you can definitely use the language model as an intermediate step to sort of decide these things. And I would guess that it would perform actually really well.
Thanks. We have another question from the audience. So Pascal, go ahead.
Yes, thanks. Yeah, to go a bit further on the structured data. So if I understood correctly, your base chunking is a fixed size. Did you try to use semantic chunking or other kind of base chunking before applying your clustering algorithm?
So we use the simplest thing. So we wanted to show that without any hand tuning or choosing any sort of very fancy chunking algorithm, that our system performs well. But obviously, improving chunking will obviously lead to better results. So we wanted to show a more general paradigm that in the most basic case of just chunking every 100 tokens and just not splitting sentences across chunks, a very simple thing to do, you can get good performance. But obviously, it's the better the chunking, the better performance. So we didn't test it with our code base because we wanted to sort of because 100 chunk tokens is sort of also standard in the literature. So we wanted to keep it comparable with previous methods as well. But you can definitely improve the chunking and it'll lead to better performance. So we didn't test it, but if you do that, it's very easy to sort of implement it in the Raptor code base, or I assume with LlamaIndex, and you can build on top. Yeah.
Okay, we just have 4 minutes left, and I do have one question I want to get in, and I'm sure this is something you've been asked, right? So what are your thoughts about long context LM and how it's going to impact RAG? This is a question we get as well. So, I have my own answers. We'd love to hear what are your thoughts. I think that's probably going to be a future that we go towards, right? As the sort of context length gets quote unquote commoditized. And like I think the way we think about information retrieval as well as summarization synthesis will have to change a little bit, especially on the interface between data and sort of reasoning engine. I think like the setting you're working with is like at 100 token limit for each of the chunks, as well as like gathering up to like 2K or 4K tokens. I don't remember exactly. But in the world where we have, like 1 million, 10 million, or even 100 million token size. How do you think about this? What are the tasks in which we should think more about retrieval, and what are ones that we should just kind of offload it to just the reasoning itself?
Yeah, I mean, that's a very pertinent question. I think my thoughts on this are, for now, I think, obviously your retrieval corpus can be trillions of tokens, right? It's still, I feel, if you look at the retro model, for example, by DeepMind, it retrieves from a corpus of trillions of tokens. So I'm not sure if it makes sort of sense to pass in a trillion tokens every time you want to, answer a simplest thing or do so. So I think retrieval is here to stay, in my opinion. I think the best way is sort of to incorporate, best of both worlds. So I think if you have, Raptor is obviously chunk size agnostic, so you can choose as long as you can embed it. And I know there are better embedding models, and I think GritLM, for example, you can sort of pass in, it can do both generation and embed at the same time. So if you have a language model that can sort of embed these documents, you can sort of think about scaling up Raptor such that you're not restricting yourself to 100 chunk tokens, but you can embed entire documents if you want to create this hierarchy tree. So then let's say I have the entirety of Wikipedia. What I can do is embed one page per chunk, and then sort of create a big tree based on the entirety of Wikipedia, for example. So I think enabling long context, I mean, enables us to think much more and think at a much bigger scale of retrieval. So not just retrieving 100 chunk tokens, but retrieving entire documents. But I think retrieval, you still sort of need retrieval for that.
Absolutely. Yeah. Well, thank you so much, Parth and Anna and everyone else on the paper. Thanks for really pushing forward like the boundaries of knowledge on RAG specifically. And I'm sure we have a lot of different future directions to explore. I guess you got either in academic or startup side. And hopefully this session was informative for the audience, and also it gave you some signal in terms of what future direction you can explore that are sort of top of mind for the practitioners. And yeah, thank you guys so much, and thanks to all the audience for attending. I think we'll close it off here.
Sounds good. No, thank you for having us. It's great, to get out to so many people, and we're excited to see what people build with Raptor and what it enables. Thank you.
Thanks, everyone.